this is Mr. T with another tutorial. Today we are going to investigate writing equations of lines that are tangent to some curve. This is one of the fundamental things that calculus was developed for. So let's get into our presentation. Let's talk first about rates of change. Rates of change, some examples might be how the speed you're driving in terms of like miles per hour, price you pay per item. Those are all rates of change. When we're talking about a linear function or something that can be modeled by linear functions, we can visualize rates of change by looking at the slope of a line. For lines, the slope is constant all along the line, and we've learned the basic formula for finding that slope of looking at the rise over run of the line. But what if the function that is modeling our real-world phenomena is not linear? Maybe it's a parabola. So let's understand, what does it mean to find the slope of a parabola? First, we're going to show a demo that kind of demonstrates this purpose. Okay, I have our demo up now. I'm using a site from Wolfram that demonstrates various mathematical concepts. Here in blue we have part of a parabola graph, the graph of y equals x squared. And we are interested in finding the slope of the tangent at point Q. The tangent line drawn is shown here in this red line. We also have another point on the tangent line that is h units away from point Q on the x-axis, and we have drawn a secant line connecting or going through points Q and P. So let's look at what happens if the distance between Q and P becomes smaller, or another way of saying that, we're going to have h down here get closer and closer to 0. So I can do that by this slider. So we can see point P moving down, and you should be able to see that the secant line here appears to be approaching the tangent line. And as we get closer and closer to Q, or another way of saying it, our value of h here getting closer and closer to 0, the secant line and the tangent line are becoming the same. Now here the point P is what we have here, what, 1/100,000th or something like that away from P, so a very small distance away from Q, I mean. And the slope is, at this point, 4.001. If we kept going, we might see that the slope is going to be 4. So this shows the relationship between secant lines and tangent lines. And our recent topic on limits, what we are doing is we are looking at what happens to the secant line, or the slope of the secant line, as h approaches 0. So let's explore that in mathematics a little further. So I now have a static picture of what we were talking about. This would be our point P and Q. This is just some arbitrary function that we have. So let's first look at and write, if we were looking for the slope of the secant line, so let's look at the secant slope. Now the secant is a line, so we can use our rise over run. So if we made a triangle here to find our rise over run, this distance, or this vertical, is our rise, and this horizontal is our run. Now let me make up here, our rise is normally the formula y2 minus y1, but the y value of point P here would be f of x plus h, and the y value of Q is just f of x. So our rise is that, and our run is the distance between these 2 points. So the x2 is x plus h, and we have to subtract that x sub 1, and if we simplify that we get h. So the slope of our secant line, being rise over run, would be f of x plus h minus f of x all over h. Now, I had you compute this in class the other day when we were working on function notation, and I was having you practice that heading into what we were going to be doing today. Now, what we saw in terms of this tangent line, we could estimate or approximate that if we move point P down along this function closer and closer to Q. And when that happened, the value of h here was approaching 0. So when we want to find when something approaches, we can use limits. So the slope of our tangent line would be approximately the limit as h approaches 0 of this expression up here. This is one of the most fundamental things in all of calculus, and we'll be using that over the next couple days to explore problems. So again, the rates of change. Our first value was x, our second value was some distance away, and we're using the letter h to represent that. And our secant line also gives us the average rate of change between 2 points, and we came up with this formula we had on the previous page. And instantaneous rate of change is equivalent to our tangent line. That's when our h is very small or approaching 0, and again we had this limit. So let's look at this to look at a sample problem. We have an equation this time, y equals the square root of x plus 1. And we want to write the equation of the line that would be tangent to that function at the point where x equals 4. Now remember, to write the equation of a tangent line, a linear function, we need to find the slope, and we need to then using a point, write the equation of the line. Well, to find the slope, we're going to use the formula that we just had a minute ago. So this is the instantaneous rate of change, or the slope of the tangent line. And I have to take the limit of f of x plus h, so I've plugged x plus h in for our radical here, plus 1, and then minus, this is f of x over h. Now when we were working on indeterminate limits the other day, when we had a radical problem, because here if we plug in 0 for h, we're going to get, at this point, if we plugged in 0, we would be getting square root of x plus 1, plus 1 minus square root of x plus 1 over 0, which is 0 over 0, which is indeterminate. Oops. So if you remember on our indeterminate limits, when we had radicals, one of our skills for trying to resolve that was to multiply by sort of the conjugate. So in this case, I'm multiplying the top and the bottom by this same expression with a plus here. So now we have a difference of 2 squares on the top, so when we multiply those together, we get the first term squared. So if you square radical x plus h, it undoes the radical, and here we have radical x times radical x, which would be x. And if we simplify the top, we get h. On the bottom, we have h times our expression here. We can now cancel out the h's, and we get 1 over 2 times radical x, because we're also putting 0 in for that. So now this is a formula for the slope of a tangent line at any value of x. Now we're interested in the particular value of x here when x is 4. So let's calculate that. So we're going to plug in x equals 4 into our formula here and calculate. So we get 2 times radical 4, that's 2, so 2 times 2 is 1/4. Now we're just going to use our skills from Algebra 1 to write the equation of the line, of this tangent line. Now to write the equation of the line, we need our slope, which we found, and we need a point. Now we were given the x value, we need to know the y value at this point. Well, that's merely evaluating this function at x equals 4. So if we plug 4 in for our x for y, or if I use function notation, we're finding f of 4. We get 3 for the y value, so we have this point. So I'm using the point slope form of a line, y minus y1 equals m times x minus x1, plugging in our point here. And then we just simplify that equation by distributing the 1/4 and adding the 3 over here, and we come up with our answer, which, again, this line, if we graph this line and we graph this function, this line would be tangent to this function at the point x equals 4. Good luck as you continue forward with this topic and work your own practice problems.